Hello everybody. So, in the last class we discussed basically Runge-Kutta for array of particles which were organized in a straight line, right, and basically we were looking at the vibration of a string which had been discretized, and the position of each of these particles was fixed, and they could basically displace along the y direction. So, this being x, right, and to solve the differential equation, suppose there were 50 particles, we would have 50 first order differential equations for the positions and 50 first order differential equations for the velocity, and we were solving them in tandem. So, there were coupled differential equations. In addition, what we had was periodic boundary conditions. So, basically the left neighbor of particle number 1 was particle number L 50 say, and the right neighbor of particle number L would be 1. So, there was essentially periodic boundary conditions, and what we are looking at essentially is basically the displacement perpendicular to the line. So, how much are they moving, what is the kind of wave like motion there is, right. And what we had said, suppose the initial condition is one of the particles, we give it an initial displacement and then we see how the wave develops. So, you have basically 100 differential equations which you are solving in tandem, which means essentially that you are recording the position of each particle as a function of time, 100 of them, and velocity of each particle as a function of time, and so on, right. The question is, how do we visualize it? Of course, we can calculate it, but how do we visualize it, and what is the code like? So, we will be discussing this in a hands on manner in today's class. One change what I am doing, since we have periodic boundary condition, what I am doing is basically not putting them in a line, you can do that as well, but I am putting them in a circle. So, the position is not along x, okay, and you will see that it will help you visualize this, because else it is difficult to visualize that one is connected to L. So, what I am doing is I am putting all these particles on a circle like this of a circle of radius r, say, right, and basically all these particles are placed on the circle as z equal to z being this direction, and suppose this is x direction, and the particles shall be displaced perpendicular to the plane of the screen. So, it is basically, if this is the circle, the particles will be displaced like this, and all the particles are placed as r z equal to r sin theta and x equal to r cos theta. This is not changing, their y displacement is changing, right. Without much ado, now let us move and show you how this particle will move in a movie, and then I shall show you the code and tell you how to make the movies, which is of course important to visualize also the data which you have generated. So, what I am going to use is basically use a software called JMOL, which is freely available and can be installed in any Linux systems. So, here I have the position coordinates of all the 50 particles are stored as a function of time in file .xyz. So, basically here you have 50 particles placed in a circle as r cos theta, r sin theta, and this direction is the y direction, and here you see that one particle has been displaced. So, the initial condition, if you remember, was that y is equal to 0 for all particles except 1, and suppose this is that one particle whose position has been displaced, the velocity has also 0 for all the particles, and because of this displacement, let us see what happens. And the way I do it in this JMOL is go to tools, this animate, and do it once. So, now what you see is this particle had been vibrating because we basically have a spring, and what we have is this vibration moves along this arm and this arm, and after some time all these particles, coupled differential equations, they start to move. I will just play this movie once again for you. So, here there was this particle which was displaced, and it displaces the neighboring particles, there is a force acting. So, they are all doing basically simple harmonic motion in the y direction, and after some point of time the displacement reaches this point, the other end, the after 25 particles. And of course, you can ask questions like how much time would it take for this displacement, for this perturbation to reach the other end. How can you change the speed of the wave propagating along this? So, this motion is the one which you basically Fourier transform and do your normal mode analysis. Here we are actually visualizing how 50 particles would oscillate, right, and you can change the frequency and so on and so forth by changing kappa, mass, and so on and so forth, right. So, well and good. So, this is how you would have visualized 50 particles, the solution of 100 different differential equations. So, to make this movie, so now what I am going to discuss is how will you land up making this movie. First of all, I will show you the code itself. I understand it is a bit involved, though it looks simple, but I will just show you the code and then tell you in details how to land up to this movie. Okay. So, just so here is the program. The program is called RK4 coupled, coupled for coupled differential equation, and here the code it is a slightly different version. I have only 20 particles, but you can easily change it to 50, no big deal, right. So, you have 20 particles in this version of the code arranged along a circle, and the number of iterations you can choose, and I have chosen number of iterations here to be 1000, and choose 10,000. Then you can watch the particles moving around for a longer period of time, look at long time behavior, but number of iterations I have chosen is 1000. H, the integration interval over which you integrate the Runge-Kutta I have chosen to be 0.02, sorry 0.02, I have denoted it by dt, and what I have put in is that initial time t equal to 0, initial time equal to 0, initial displacement I have put it equal to 0, initial velocity equal to 0. The positions and velocities are stored into arrays called VIM, and the length of these arrays is NOP. NOP is number of particles, which is 20. Km is 1, kappa is 1, and mass is 1. So, all those things have been chosen. Then the initialization of position and velocity. So, basically I say okay, time equal to 0 init, then YIM, this is that array, all of them is equal to 0, init y has been defined to be 0 just here, but only the first particle YIM, the first particle, the displacement of the first particle in the y direction has been given to be 0.8. You can just give it to be 0.3 as well, does not matter. Initial velocity, this is also an array. Remember, VIM is an array. So, all the 20 boxes in that array have been defined as init well. Init well was 0 here. For ease of calculation, I have defined quantities like dt by 2, h by 2, which we use in our Runge-Kutta method, right. I do not want to calculate this every time, it takes computing power. And here what I have done is basically to put particles in a circle. It is 2 pi. So, this 2 pi has been divided by 20. So, that basically you change theta 20 times and you have the position of each of these particles by taking r cos theta and r sin theta, no big deal. So, that is the x and z direction. If you had 50 particles, you would divide 2 pi by 50 and put the position of each of these particles, 50 of them at theta equal to theta 1, theta 2, theta 3, theta 4 up till theta 50, which would complete the circle, right. Fine. So, that is the basic initialization. Here I am calculating all the different values of theta I, which will be there for 20 particles. Here is the actual code. Do I equal to 1 to niter, niter being number of iterations, which I have chosen to be 1000, you choose it to be 500, 10,000, whatever. Time is being incremented by time dt, right. Dt will be 0.02, that is what I have chosen. And then what I am doing here, there is this loop. So, from kk equal to 1 to number of particles, that is exactly what we discussed, right. Loop of number of particles. So, you have to identify the neighbors. So, suppose kk is equivalent to I in my previous lecture. So, ith particle. So, here you are talking about the kkth particle. Then the two neighbors on the two sides are kk plus 1 and kk minus 1 here, but you have to be careful of the periodic boundary conditions. If kk equal to 1 is the first particle, then the neighbor on the left is L, L is number of particles 20 here, right. If kk equal to number of particles, which is the last particle in that chain, then the right neighbor kk plus 1 is equal to 1, right. That is how you do your periodic boundary condition. Here I am calculating f0 kk for each of the particles. The loop is over kk, and that is f0 for the position. So, dy dx equal to Vim. So, f0 is nothing but dy dt, that is Vim kk, that is what I have written, and this is for dv dt. So, you have to calculate f0 v, which is nothing by km, and that entire formula that we showed. This is the right neighbor, this is the left neighbor, and this is Ym kk itself. Then what do we do? Then we basically calculate y1, okay, refer to your previous lectures if you have forgotten what it is. Y1 to be, you update it by dt by 2, right. Dt by 2, dt is the same as h by 2, and similarly you update v1, you update the position, this temporary position, and you update it. So, v1 is also updated by dt by 2. So, you have updated the positions and the temporary velocities of all the particles. So, temporary position and temporary velocity, just to calculate the local slope after having incremented the position and the velocity or any variable. Here at these new values of y1 and v1, we are calculating f1k and f1k and basically f1v, right, for all the particles. So, there is a loop, over all the particles. Again we identify neighbors carefully, keeping in mind periodic boundary condition. Using this f1, we calculate y2 and v2. So, this is again some increment by h by 2. After calculating that for each of the particle, we calculate essentially the next one, which is f2 for each of the particles and f2v for each of the particles. Then we calculate the new positions and so on and so forth, right. So, this goes on, and after calculating f0, f1, f2 and f3 for all the particles, what we do is, this is your actual position update. Those were only basically incrementing y1 to different values and then trying to calculate the averaging of these slopes. So, this is the one where we actually update. So, this is the actual new position of the particles, which is Yim, which was the initial velocity at beginning, into dt into f0 plus 2 f0, f1, 2 f2 and f3, except remember that F3, F2, F1, F0, all of these are arrays, and similarly YIM is an array, right. So, Fortran allows you to sum all the elements of the array like this, and you can even calculate the force. What is the total force? You can calculate acting on each of these particles. Force is also an array, and then this is an update the new velocities, the other set of differential equations, where all of these are of course arrays. VIM is an array. So, what do you have? You have the position and the velocity of each of the particles after time h, right, which are stored again in YIM and VIM. So, using that we can now calculate the new position and velocities at time 0 plus 2 h, right, and this entire process will go on in a loop depending upon number of iterations. Fine, but to see this data we need to save the positions and the velocities at each time to be able to see the movie, right. Okay. So, even before saving the positions, what I have done is basically calculate the kinetic energy for each of these particles. Here Ke is equal to Ke plus half into VIM into VIM, half mv square for each of the particles, and similarly I have calculated the potential energy for each of these particles, and basically write down as a function of time the total energy, the kinetic energy, and the potential energy of all the particles. And you know that the total energy has to be conserved. It has to be absolutely straight with an error of 0.02 to the power of 4, RK4, right. So, this is just for a cross check that you are maintaining your energy momentum conservation. You can similarly check for the momentum of the particles, and that has to be should be 0, right. And after that what we are doing is using, so what we want is that we want to save the position of all the particles at every say 10 steps. So, there is no point in saving the position of all the particles every step, because in one step after one iteration h equal to 0.02, the particles would have moved relatively little. So, to able to visualize the motion, you do not want to basically store the position every time step. You might, you may if you want to, but it would make more sense to basically store the position of the particles every 10 iterations. So, you can see the particle movement when you make it in a movie. So, what you want is the position of each of the particles should be saved in a file with a time label, right. So, suppose you say that your file name, primary name is suppose position, and then after 10 iterations you want to save it, you want to add the word 10 to the character variable position and say okay, the position of all the particles are saved after 10 iterations in the file called position.10. Okay. Similarly, the position of all the particles after 20 iterations are saved in a file say called position.20 or underscore 20. The position of all the particles after 30 iterations are saved in a file called position.underscore 30. So, then if you have the position of all the particles at different instances in time, then these data you can all join them in one file and you can play the movie. So, the question is how do you do it? For that you need the position of all these particles, and I will tell you how to first of all add suppose any string is there, any character variable position, and how do you add an integer 10, 20, 30, 40, so on so forth. And here what I am doing is basically writing down at every instant in time. I am opening a new file. Okay. So, file equal character A, where the value of character A shall keep on changing at time. At one time it will after 10 iterations it will be position underscore 10, after 20 iterations the value of character A will take position underscore 20, after 30 iterations the value of the character A is a character variable, string variable will be positioned underscore 30. So, every time though I am using the same loop, a file will be opened with a different name, and within that I am writing down N. N actually stands for nitrogen, because the software that I will be using, JMOL, basically it is a chemistry software. So, it needs to be told which atom you want to plot. For us, we do not care about atoms, we just care for the sphere, right, or a point particle. So, N one has to put just to say nitrogen, you can put in oxygen, it will just be denoted by a different color. Then r cos theta, r sin theta corresponding to x and z, and those will be unchanged with respect to time, but so the loop is over number of particles. For each particle the value of this and this will be different, but the y, this value for each particle will change as a function of time, right. So, as you saw in the movie, the position of all the particles along the circle remain the same, but all the displacement was only perpendicular to the plane of the circle. So, this, that is why this quantity and this quantity will remain fixed as a function of time, whereas y I m will change. That is what you are calculating as a function of time anyway. And similarly, if you want, you can also write in the velocity, then you close the file. The question is, how did I do this addition of a number 10, 20, 30, 40 to some variable string variable, say position, just to show that part. So, that part I do here in a subroutine. Okay. I will not show you the subroutine, but I will teach you how to do that, and that is done in. So, this is a test program which you should try out, and then this same lines you can just put in a subroutine called add number to string, right, and each time its variable, the character variable will be different. So, here you have a character variable called file name, you can call it character A, does not matter, called file name, and that is of length 30, right, and suppose do I equal to 1 to 100, this is equivalent to number of iterations. If mod I 10, so I keeps on changing from 1 to 100 or 1 to 1000 or 1 to 10,000 number of iterations, and every time that mod I comma 10 equal to 0, that will happen every 10 steps, then you say I unit equal to 10, okay. And if you write this line, write file name, okay, and whatever you put. So, here I am teaching you the method, whatever you put between this double comma and this double comma, okay, and here this is I 0, you write it I 0, this stands for integer, and here you are writing I, right, this is what was changing. So, only if this it will enter this line only every 10 steps, right, and if you run this, you will see that you will get a variable called position, value of I 10, 20, 30, 40 dot xyz, right. So, so here you have written position, then I 0 here after a comma, and this value, different values of I will be written at this position, right, and then dot xyz will be added. I have already run it, you can have a look. So, basically if you So, basically if you run it, you will have position 10.xyz, position 20.xyz, position 30.xyz, and so on and so forth. And if you had given I equal to 1000, then you would have 100 files with these different names, each with an ending .xyz, right. So, that is how you add numbers to strings. That is the general principle. If you did not have that .xyz at the end, then that would not have been added, you would have got only position 10 or 20. And if you had put in an underscore such as like this, let us compile. Now, you have some other files with position underscore 50, position underscore 60, position underscore 10, and so on and so forth, right. So, you can even put in names at the end. Why I did XYZ, I will explain in a second, right. Basically JMOL, the software JMOL with which I made the movie accepts files, recognizes files only if it ends in .xyz. Okay. So, position underscore 10 gives you basically the time index. It tells you that you are storing the position at time 10, 20, 30, 40, 50, and you have added .xyz because, or it will allow the software called JMOL to basically to recognize the files, and it can be uploaded. So, what you do is essentially, so in the coupled differential equation I have basically generated these coordinates, just let me go to 50 particle PBC. It has just the same thing, it has the same kind of names, and I am storing the position of these 50 particles in at various instances of time, right. So, you here you see 10, 100, 1000, 1010, 1020, here 110, and so on so forth. And of course, I have times at time 120 and time 20 here and 30 here and 40 here and so on so forth. What is inside the files? So, here is the nitrogen, these are the position, this is the x coordinate, this is the z coordinate, and this is the y coordinate, which keeps on changing after each time. So, these first two columns, sorry, the first three columns including nitrogen, they will remain the same, but this column, the fourth column will keep on changing at different times, it will have different values. Okay. Now, what one needs to do, you have these files at different instances of time. Now, they have to be basically added together, okay, to make one big file. How does one do that? One can do it mechanically, but there is another subtlety here if you want to make the movie. Basically, what first of all, you have to make these into XYZ. So, the JMOL will not be able to recognize a file like this. You have to name it something like XYZ, and you must also tell JMOL how many particles are there, because the JMOL the software does not know that you have run the code with 50 particles. You could have 50 particles, 20 particles, 100 particles, it does not know. So, what has to be done is you write that there are 50 particles. So, the total length of this file becomes 52, right, in VI. So, this is 50 particles, give a gap, this is important, and then you have the position and coordinates of 50 particles. Then each of these files can be added up into one big file, which I have done, which you have to do it for each of the at the top of each of these files you have to write 50. Now, if you are doing it for 10, 20 files, doing it manually is possible, though boring. But if you have to do it for 1000 files, you want to add them together, you really do not want to do it manually. That is, open every file, write 50 on the top, then save it, then go to the next file, write 50 at the top and then save it. It is too boring. You can mechanize it, at least in Linux, you can mechanize this entire step. What I have done is basically write a file called AA, where you have nothing except 50 and a blank line. Then using the cat command of Unix, I am adding. So, please look up what is the cat command in Unix. Cat AA, then this file where I have the position of all these particles and nitrogen written. So, I am adding cat in cat stands for concatenate. So, add AA, or rather cat AA and this, and store it in file A1. Then cat AA and the second position and store it in file A2. Then you do it for the third and the fourth and the fifth and the sixth and the 10th file, which is stored in A10. Then you cat A1, A2, A3, A4, all of these in file 1.xyz, right. Similarly, for 110 to 120, you keep on adding AA to each of these files. Try it out what cat does, and then again concatenate all of these 10 files to file 2.xyz. So, what does file 1 and file 2 etc. have? So, just to show you. So, let us look at what does A1, A2, A3, A4 have. Vi A1, A1 it has been concatenated and this 2 has been mechanically added. You do not have to do it each file by file. You just write that file and you run it, you will get A1, and similarly you have A2. So, this is 50, but this has the y coordinate at time 20 and this has the y coordinate at time 30 and so on and so forth, right. Now, if you remember, I was adding each of these files and writing it in file 1.xyz. What does file 1.xyz have? It has 50, but after that it has again. So, this is basically the position at time 10. From here you have added A2. So, this is basically the position at time 20. And this is the position at time 30 and this is the position at time 40. So, where you have basically added all of individually each of these files A1, A2, A3, A4, A5, right, and created file 1.xyz. Similarly, you have created file 2.xyz, which is basically the position of all these files from time 110 to 200, and then file 3.xyz will have the position of all the particles from time 210 to 300 and so on and so forth, right. So, you have basically file 1. So, basically you have all these different file 1, file 2, file 3, file 4, and you can now concatenate all of them, this file 1 to file 1.xyz, file 2.xyz. You can concatenate all of them at the end, concatenate all of them into file B, say, or file A. So, one file, right, and this is the file. So, how do you run Jmol? You type in Jmol, and whichever file has all the movies over say 10,000 iterations. So, that has all been made into one big file, and jmol file dot xyz. So, this in my case it is file, I have just named it file when I previously prepared it, right. You can whatever name. So, it is a concatenation of file 1, file 2, file 3, file 4 and so on so forth, jmol file dot xyz, and if you do this, just type this in, you get this movie, and then you just rotate it, go to tools, animate once, and you have your movie. What is the message? Even if you had 100 particles, you could automate this entire step of concatenating, of storing the files, concatenating them, and see it in JMOL. You can visualize your data in a movie. Of course, for quantitative analysis, you also need the position of y for each of these particles as a function of time. You could also choose to write it not that you write the position of all the particles at a particular time. The other hand, you could also say that in one file I shall write the position of one particle as a function of time, right. Then also you can also do that in a very similar way that I wrote, where basically suppose pos 1 would dot dat instead of dot xyz would have pos position of first particle 1 for first particle dot dat as a function of time. So, you can just use that add num to string. So, it depends upon which number you want to add, and you can also save the position of each particle in a different file as a function of time. At the moment, what I have done is written down the position of all the particles at a particular time in a file. Depending upon what analysis you want to do, what you want to do with the data, you can also write it the other way, right. What I am teaching you is how to solve the differential equation. So, that you have x rather y, all the particles as a function of time, and your physics of the problem will tell you what you want to do with the solution, right. And basically this will take a bit of time for you to get adjusted, because the code was involved. After that, you take the data, do some processing to do it, to plot it in a movie called JMOL. Just install it, it will take some time, but you will get used to it. Okay. So, if you have further questions, you can always ask the TA. So, I decided to add a bit of addendum which will help you to make the movies, to explain the various commands that I used to compile the file, which was used to finally plot the movie in JMOL. So, first of all, I will explicitly show you the commands of cat. So, suppose you have two files, suppose F1, which has suppose A written and BB whatever written, and another file called F2, which has some numbers written, right. It does not really matter. And what cat does is, if you cat F1 and F2, basically what it does is write down the contents of file F1 and then the contents of file F2. So, here I made a mistake, but here if you see, it has written down the contents of file F1, and here is the contents of file F2. Now, if you cat F1 and F2 and save it in some other file, say F3, then you do not get the output on the screen. Instead, if you open F3, you will see that the contents of both the files have been concatenated and saved in F3, and this is exactly what I am using in this file called move. So, what I have done here is cat concatenate AA, and just to remind you that AA contains the total number of particles in the simulation, which is just 50 and a blank line and nothing else, and move this file, and this file say basically saves the coordinates of all these 50 particles at different times, at times 10, 20, 30, 40, 50 and so on so forth, right up till the length of the movie. And this cat command is basically adding 50 and a blank line to the position file and saving it in A1, and then saving it in A2 and A3 and A4, and all these commands have been written in a file called move, right. So, in move has all these lines, and then basically A1, A2, A3, A4 etc. are themselves being concatenated and saved in a file called file1.xyz, and then from 110 to 200 again I am saving them in A1, A2, A3, A4, A5 to A10, and this in turn is being saved. So, basically the positions of all the particles from time 110 to 200 is being saved in a file called file2.xyz, and the position of all the particles from time 210 to time 300 are being saved in a file called file3xyz, and so on so forth. And right at the end, what I am doing is concatenating file1.xyz, file2.xyz and all of these into a file called fileb.xyz. So, basically file B has all the positions in the right format of all the particles from right from time t equal to 10 to time t till say time t equal to 2000, and so all those have been concatenated appropriately, right. And then one can use file b.xyz or even to basically plot the movie. Just to show you what does file b.xyz contain. It has this 50 blank, the nitrogen, which is already I am saving in the code, and the positions. And if you go to 50 lines, after 50 lines you again have 50 and so on so forth. Now, so all these commands have been written in this file called move, right. But this is not an executable file. So, if I just make it executable by writing chmod plus x, this is a Unix command, move. So, from this text file in move it becomes an executable file, right, and now I can execute it. It is only after this step that I can execute it, and it will automatically create file b.xyz and file a.xyz, which I can now upload and make the movie and see the movie in Jmol, right. So, basically what I have done, instead of type so many commands which are written in move, type it every time, I have saved them in a file called move, made it executable, and I just type move and it gives me the the file which can be used as a movie. Now, if I change the conditions, if I change the solution of the differential equation and appropriately, suppose I give it a velocity and so on so forth, I will have a different set of coordinates at different times. In just one step, this dot move, I can make the corresponding movie file dot xyz and plot it. Okay. So, this is, I thought I would just add a primer to whatever is shown in the main lecture. Thanks.